Multilayer networks. Networks that we use in practice typically have multiple layers, not because of biology, but instead because of mathematics, as we're about to see. In 1900, a leading mathematician, David Hilbert, published 23 then unsolved problems. This was a guide and inspiration for the next century of mathematics. Many have been resolved, although some are still unsolved. The 13th of Hilbert's 23 problems implies an answer to what type of network for artificial neural networks. Here's his original problem. Are there continuous functions of three variables that are not representable by a superposition of composition of functions of two variables? We think in a little different format. Can a continuous function of n variables on a bounded domain of n space be written as sums of compositions of functions of one variable? For example, here we have a function of three variables, x, y, and z. Can we write this as a sum of compositions of functions of one variable? And actually we can. So f of x, y, z is the sum, j equals 1 to 2, of h sub j of the sums g of x, g sub j of x, g sub j of y, g sub j of z, where h1 is x cubed, h2 is negative x, g1 is x, and g2 is x cubed. Kolmogorov proved a theorem that essentially solved Hilbert's 13th problem, and in a modified version it says any continuous function of n variables can be written as the sum of functions of sums of functions of one variable, where the h and the coefficients w depend only on the function f. In other words, we can choose any g's we want to. And notice this begins to look like an artificial neuron. And many people noticed in the 1980s this neural network connection between Kolmogorov's theorem and artificial neurons. In 1989, Sabenko formalized this into an actual theorem. So if sigma is a continuous sigmoidal function and I sub n is the n-dimensional hypercube including its interior, and x is a variable in I sub n, so x is between 0 and 1 inclusive for all I equals 1 to n, then if we have an absolutely integrable function mapping I sub n to r, then for all epsilon greater than 0, there exists a possibly very large integer n, real constants alpha 1 to alpha n and theta 1 to theta n, and real constant vectors w1 to wn, such that the absolute difference of f of x and the sum j equals 1 to n of alpha sub j sigma w sub j transposed x minus theta sub j, that difference is less than epsilon. And we can actually think of this in terms of multi-layer neural networks. So given this f, we can choose parameters so that we have an f hat of x1 to xn that's approximately f, where f hat is this sum j equals 1 to n alpha sub j sigma w sub j transpose x minus theta sub j. And let's notice that this first layer, x1 to xn, feeds into a set of hidden layer, or a set of neurons that receive the inputs from all these x1s to xn's. And each one of those is then going to fire based on its input, and the input to the jth is going to be w sub j transpose x minus theta sub j, and so the sigma function fires on that and produces psi 1 to psi n. And these are the outputs from this intermediate layer. Because then we're going to have an output layer, in this case just one neuron, and we're going to multiply those outputs by alpha 1 to alpha n, and that's going to produce an output y, and that output y is simply the sum of alpha sub j psi sub j, but that is just our Sabanko universal approximator. So therefore, a neural network is a universal approximator. We don't even need continuity for what we're approximating. All we need is absolute integrability in the Lebesgue sense. And with the right parameters and network structure, that means an artificial neural network can approximate almost anything. However, it does require arbitrarily large n, that's the number of neurons in the hidden layer, and unfortunately overfitting becomes a bigger issue as n becomes larger, and therefore overfitting is a big issue with the neural networks. However, this means that we can use multi-layer artificial neural networks as classifiers. So given features, we define an f, such that f is 1 if the observation with feature x is in class 1, or 0 if the observation with feature x is in class 0. Sabanko says that any such function f can be uniformly approximated to within epsilon by a multi-layer neural network, as long as we have a sufficient size and number of hidden layers. And again, all we require here is that f is absolutely integrable. In other words, we can compute the integral of its absolute value. Most of the time we're going to work with the model we've just shown, an input layer, a hidden layer, and an output layer. The output layer could be single neuron, and of course the hidden layer is theoretically arbitrarily large, which means overfitting is an issue. So we're going to look at this three-layer neural network as producing not just a single output y, but multiple outputs y. And therefore on any bounded domain, because we can always pre-processing map to the unit interval, to the unit hypercube in n dimensions. And so therefore we can approximate any integrable function on a bounded domain by artificial neural network. We often add a constant -1 input neuron because this allows the threshold to be a weight. So we can think of the threshold as being -1 times the weight theta sub j. And so if we add thetas as synapse weights and put a constant -1 input, then we can actually think of each output as simply being firing on W sub j transpose x without the threshold, because the threshold theta has been included by putting this special neuron in. Now, we don't have to use firing functions on outputs. If we do have firing function on the outputs, we tend to use a threshold of 0. So let's look at this in vector form. So W here is going to denote the matrix of synaptic weight vectors between the input and hidden layers. So these vectors, W sub j T transposed, correspond to this capital W. We define a vector firing function to be capital sigma, vector sigma of capital W times x, to be the vector of ordinary scalar firing functions applied to the W sub 1 T transposed x up to the W sub n transpose x. Also, let's assume that we're firing on the output layer. So y is actually sigma of this. Then we can rewrite this three-layer neural network in vector form by noting that if the vector y is the y1 to y sub m outputs and a is the alphas, then we can write y equals vector sigma firing on matrix A times vector sigma firing on W times X. And this allows us to extend these ideas to multiple layers. So we start out by saying that Y is sigma of W sub L of X sub L, where capital W sub L is the synaptic weights between the last hidden layer and the output layer. Then we move back one layer, X sub L minus 1 and W sub L minus 1. And we can continue moving back. And if we move all the way back, then we can write a multi-layer network generalization as a vector firing of a matrix, of a vector firing on a matrix, on a vector firing on a matrix, so on and so forth. In other words, it's just a nested sequence of compositions. Now, artificial neural networks, when you use these layers, are universal classifiers. They don't rely on assumptions like linearly separable. They can overfit the training set, and I will be repeating this many times, as I probably have already. So let's look at an example. We saw in the very first lecture that the XOR is not linearly separable in 2 dimensions. The AND is separable. In other words, if the class is 0, if only one of X and Y is 0, and 1 only when both X and Y are 1, then we can plot those on a 2-dimensional grid like this, and we can separate those with a straight line. Or can also be separated by a straight line. But the XOR, in which if the X and the Y are the same, they're class 0, and if they're different, they're class 1, that can't be separated. So what do we mean by linearly separable? Well, a classifier would implement the XOR if there was some threshold for which C of 0, 0 and C of 1, 1 were both below the threshold, and C 1, 0 and C 0, 1 were above the threshold. Logistic regression is a classifier that uses, in this case, the probability x1 comma x2 is that sigma function with the linear exponent negative w0 plus w1x1 plus w2x2 for the appropriate coefficients w0, w1, and w2. But no choice of the coefficients would result in an implementation of the XOR as we have here. So there are many classifiers that can't implement the XOR, in particular those that require linear separation. But there are many classifiers that can implement the XOR. K nearest neighbors, we can just construct a graph where the 1 class are all neighbors and the 0 class are all neighbors. We don't know what metric to use exactly, and so, or what measure of distance, and so this is difficult to generalize. A 3-layer artificial neural network also implements the XOR because we can simply assign negative 1s to the cross synaptic weights, 1s to all the other synaptic weights, and a theta of 1/2, and that actually implements the XOR as a 3-layer artificial neural network. It's difficult to produce this via iterative training, however, as we'll see later. So are there classifiers that readily implement the XOR? Well, of course. The 3-layer artificial neural network with a hidden layer increasing in size. Artificial neural networks with more than one hidden layer can actually implement the XOR readily without any difficulty. Support vector machines, which are related to logistic regression, but in a high-dimensional context. And all these techniques are techniques that look to increase the dimensionality of the classifier. More hidden neurons, more variables, higher dimensions. So let's look at an example from the IPython notebook. We're going to look first at the XOR data that you see here, and we're going to classify it using logistic regression. And what we'll see is that the logistic regression maximum entropy approach produces coefficients that are all 0. So W0, W1, W2 are all 0, and not surprisingly, it predicts everything in the XOR is all zeros. In other words, we can't implement the XOR using logistic regression. But how about if we use an artificial neural network? Well, we have to train it. You see a training here. And notice now that when we actually apply it, simulate it, then we get the correct classifications. And we can choose, of course, here a threshold of 1/2 even. But you can see the relationship here. Now, let's look at another example of an artificial neural network as a universal classifier. We're going to place two classes of dots in a two-dimensional plane. And remember that logistic regression, we did this with the iris data, and it's separated only with straight lines. But an artificial neural network can find arbitrary separating curves. Of course, this means artificial neural networks can have a problem with overfitting. So we're going to look at this using a really nice applet by Jeff Heaton of Heaton Research, used here by permission. And we're starting out with a neural network with a hidden layer of size 20. And what we're going to do is we're just going to put a whole bunch of green dots. And then we're going to use these green dots as class 1. Then we're going to put in a bunch of red dots, that's class 0. And then we're going to classify each point in this grid as either red or green after we've trained the neural network. And you can see this was pretty much linearly separable, and the neural network did a good job of linearly separating the two classes. But let's add some more red points so that it's very obviously not going to be a linear classifier problem or a linearly separable data. The neural network actually just continues training from where it was, and in a relatively short period of time it adapts and separates correctly the two training sets. Now, what this means is that we can actually use a neural network even when we don't have linearly separable data. And it's pretty consistent. But let's suppose we do this again, because you could argue, well, that could be transformed to linear. Let's look at something that you couldn't transform to linear. So I'm going to put a bunch of red dots in here. And then I'm going to surround them with a bunch of green dots so that very clearly it would be very difficult to translate this into linearly separable. But notice the neural network does a good job of converging once again. And it correctly separates the two populations, the two classes, the red from the green. But now let's make it even tougher. Let's add some vertices, some points inside the red region. And this, of course, is a lot tougher. So we're going to run 2,000 iterations, and you'll notice this is a hidden layer of size 20. And we run for 2,000 iterations, and you can see it's really struggling. However, that's okay because the theorem says we have to have n going to infinity. In other words, we might have an arbitrary large n. So now we have a hidden layer of size 50. And with a hidden layer of size 50, then in 2,000 iterations or so, it can separate the two, the red population from the green population, even though clearly they're not linearly separable. And we don't use artificial neural networks just for classifiers. So classifiers are a type of problem that we've emphasized, but it's not the only kind of problem that we're interested in. For example, we can use artificial neural networks for curve fitting, for parameter estimation, even for signals, as filters in signal processing. Let's look at another little example here. This is a curve fitting example. And so we see that the green neural network output does a decent job, at least qualitatively, of approximating the actual data. In fact, neural networks can think. They can be trained to make decisions and even be trained to classify information. Here's a little neural network chip, as a matter of fact. So in summary, artificial neural networks are universal classifiers. Their form is inspired by biology, but their function is defined mathematically. And they tend to be defined by multipartite directed graphs, layer to layer to layer to layer. It's not necessary to use such a topology, but there are good reasons for such graphs. But there are some disadvantages also, as we'll soon see.